doesn't necessarily have to do with conversions. And it turns out that pretty much everything we do in chemistry is conversions. Okay? We may package it slightly differently and sell it, oh, it's moles, reactions. Ultimately, all we're doing with those is generating a conversion factor. Right? So what we want to go back and do is take a look at what's happening within dimensional analysis. Okay? So our approach, if we broke this down stepwise, would be to start with our desired unit. What are we trying to get to? Always write that down. Okay? When you step out of the house, you don't just randomly walk around and go, oh, grocery store, I should buy some food. Okay? You probably stepped out of the house, that front door, saying, I need to go to the grocery store because I'm hungry. Okay? Have a target in mind. You don't just randomly walk through the streets. You didn't randomly walk into Chandler Gilbert and go, oh, maybe I'm going to take a chemistry class. Maybe not. Let's see what happens. Let's see what room I walk into. There was a goal. Okay? Make sure you know what that goal is, even when it comes to solving our questions. Okay? After that, we need to know what we have. What information are we starting with? You may want to go to become a doctor. Right? That's your desired end goal. What information do you have to start with? Well, I know nothing about being a doctor. Well, start with the desire and say, how do I convert that desire into becoming a doctor? I need to take X classes. Right? I need to pass these classes. I need to achieve this grade. You're adding those steps in to get to that desired goal. Right? So we want to know what we're starting with as our step 2. And then as our step 3, we're building in those conversions. How do we upgrade our knowledge to get us to that final system? Right? And that's dimensional analysis. That's what we've been working with, and that's kind of the process behind it. Okay? We're still fighting that process, at least that's what I'm seeing. Okay? Maybe you aren't. Okay? Maybe there's other parts that are missing, and that's partly why we're repackaging it here. Okay? So that convert A to B is coming from an equality. Okay? Where we're saying whatever A is somehow equal to whatever B is. That was our given information. So if we look at the first sheet, or the front of that exam, we notice that there's a bunch of equalities. I think the first one is 1 inch equals 2.54 centimeters. Okay. Extra irritating because I wrote out centimeters, right? Okay, as opposed to giving you the abbreviation. Right? So there's an equality. What could we do with that equality?
We can do, like, we can reverse it, right? We can do 1 inch on one and 1 inch on the top. And then...
Let's say I want centimeters, but I'm given 5 inches. How would I convert?
You just put the inches on the bottom.
Okay. I need an inequality, or I need some information that relates inches to centimeters. Right? Well, what's the number in front of inches from our equality? 1. The number in front of centimeters is 2.54. So we're taking that information and immediately dumping it in. Well, why can we dump that in? Why is that allowed? Can I divide both sides by 1 inch?
No.
That equality. Am I allowed to do that? Right here. Can I divide both sides by 1 inch?
No.
Okay. So no starts to tell me something that we're missing some of the mathematical background behind this.
So
yes.
technically you can, yeah.
I can absolutely do that. Okay. 1 inch over 1 inch, right? Which would be 2.54 centimeters, which I'm going to write out the abbreviation now, over 1 inch, right?
Mm-hmm.
I did the same thing to both sides of the equation. I'm allowed to do that. That is perfectly valid. Okay, and that goes back to our mathematical reasoning from algebra. If you have questions on that, you should talk to me after class to make sure we address this. Well, why would I do that? Well, what is 1 inch over 1 inch? The whole point of that system is I now know that this is 1. 2.54 centimeters is 1 inch. 1. So when I go back to my equality, and my dimensional analysis down here, we say, well, why could we do that? Well, what is 2.54 centimeters?
1 inch.
do I change the meaning of 5 inches by multiplying by 1? The value. No, I don't. Okay? But instead of multiplying by 1, I multiply by this thing that I know to be equal to 1. I again don't change the meaning, but I can change the unit. I can change the system by which we measure that meaning. So all of our conversions, every conversion thing, that convert A, convert B, 2.54 centimeters over 1 inch, all of those are 1. Every single one. Okay? That's why dimensional analysis sets up. Because all we're doing is multiplying by 1. Okay? Why would we do that? It's because we're trying to change the frame of reference. Okay? How are we observing that? We've come up with a system that allows us to convert the different observations from one point of view to another. I think that's kind of neat. Okay? Kind of, sort of? Okay. So we use it because we can rearrange it to make 1. So what are some conversions?
Are you talking about the ones on the paper you give?
Well, any conversion you want to give me.
Okay. 1 mile is equal to 5,280 feet.
Anything else? Anybody else have any other conversions?
Ooh, let's do 1 AMU equals 1.66 times 10 to the negative 24 gram. So.
I would argue both of those are really hard conversions. Why are both of those really hard?
Deal with big numbers.
Okay. Really big
Or
numbers.
really, really tiny
Well,
numbers.
that's what I wanted to do.
3 feet equals 1 yard. 12 inches equals 1 foot. Where did you get those from? Right. You may have gotten the miles to feet and even the feet to yard, okay? Or not the feet to yard, the AMUs to grams from the sheet. Okay? How about the feet to yard? Did you get that one from the sheet? Some of you already knew that, right? How about inches to feet? You already knew that. Okay? You have that knowledge already. It's now a question of manipulating it and using that in our dimensional analysis, setting up those unit systems to go through and work. Okay? So the next part that then confuses people when it comes to chemistry is now, okay, we're formalizing using our dimensional analysis to come up with these solves. But now the next part is we throw in some weird conversion factors, like of course the one Lauren gave us. 1 AMU, that's not too bad. I don't know what AMU is, but 1, that's okay, equals 1.66, whoa, decimal point, times 10 to the minus 24. Powers of 10 and a negative power of 10 at that. Okay? That conversion factor now loses all meaning for what we can grab a hold of. Okay? If we trust it, like we trust that 3 feet equals 1 yard or 12 inches equals 1 foot, it's no different. It has the same value or it has the same ability to go through and do our dimensional analysis. Okay? This is why we did our initial conversions with those simpler conversion systems. Okay? Not so that you could prove to me that you can convert inches to feet. Okay? I assumed you knew that already. What I wanted you to do was to come up with that process. Okay? That process is what we have to keep working with. So when we're looking at these conversions, okay? We had those conversions already. You knew them in your brain. Okay? What happens when we move up to chemistry? We start incorporating these other bizarre conversion systems, the AMUs to grams. What do you have to then do with that conversion factor? You could have to memorize it, right? Okay? So I simplified some of that and said you don't have to memorize it, it's on the exam. You now still have to use it, but that's still relying on the old stuff that you've already had. Are there conversion factors that we've talked about that are not on the exam? How many sodiums in sodium chloride? Is there a conversion factor for that?
Mm-hmm.
Yeah, what's the answer? How many sodiums in 1 sodium chloride?
2.
So I need to know my nomenclature that sodium chloride is NaCl, and if I look at 1 molecule of sodium chloride, I need to know that I have 1 molecule, or sorry, 1 atom of sodium. How do I know that information?
Because NA is one charge, they're balanced. And
I'm reading that out of the chemical formula. Right? And you're right. I have to make sure that chemical formula is balanced and correct. That's nomenclature and building all of that. Right? Could I go through and give you that conversion factor, that equality? Yeah, I could. How many substances are in the world? Is probably a reasonable statement. A lot. Right? Your exam would probably fill up more paper with just all of the individual conversion factors than we could possibly fit in this room. Okay? And that's one copy of the exam. Okay? So you're responsible for being able to figure out what those formulas are and then being able to interpret those formulas. Okay? That adds a layer on top of this because you now have to come up with that conversion factor, that interpretation. You have to remember where to find that conversion factor. Right? What if I want to convert hydrogen gas into water? Can I do that through a chemical formula?
Just hydrogen gas?
I just said hydrogen gas into water.
No, you need other things.
I'm missing oxygen. Right? Hydrogen gas is not water. Those are entirely different substances. Yes, hydrogen might be in water, the element, but not hydrogen gas. It's a different system. I would need something else to allow me to do that conversion. What would I need? Right? Just oxygen. So I take hydrogen and oxygen and now I have water.
so you're going to get poisoned. Yeah.
So I just take hydrogen and oxygen and I have water.
No.
Right? I would need 2 hydrogen, 1 oxygen to produce 2 waters. I have to come up with that balanced equation. I now have an expression that allows me to convert hydrogen into water.
So I guess that's kind of where some people could mix up, is if they see water, H2O, they
Yep.
could easily immediately say there's 2 hydrogen atoms, but really there's 4 hydrogen atoms.
So the equation brings in a whole nother layer of systems where we can run into issues and difficulties, right? Because we could go through and just say, well, isn't it just 1 hydrogen is 1 water? Well, is that equation correct? Does that left equal the right?
No.
No, what's wrong with it?
They're not balanced.
How could I balance it? There's an interesting question. How could I balance this?
With an H.
So one option is to add more hydrogen to account for this, which then means we have to add more water because the oxygens didn't balance. Couldn't I have also just written O?
No.
Isn't that balanced? I have a leftover oxygen atom. It's a leftover piece, right?
Oxygen can be a single kind of
Okay. There are rules that we stack into this. Oxygen can't exist on its own. It has to be in a molecule form. So that already is problematic by showing that. Okay. The other part of this is in that creation, or the creation of this equation, we are making what massive assumption?
With
I have
the product side?
one of these and one of these. That's why this works. What happens if I start with 2 hydrogens?
Then you'd have 2 H2O.
Okay. That now changes my equation, right? 2 hydrogens and I'd have 2 H2Os and I wouldn't have any more oxygen left over. So the instant I change the amount of the element, what happens?
You get more bikes.
I have a new expression to explain what I'm observing. What if I change the amount of oxygen now?
You only had 2 items because nothing changed.
You still have 1 bike.
Still have 1 bike.
Is this equation now valid? No, so what has to happen?
You have to add back in that.
I have to add in another oxygen. Right? So every time I change the number of particles I'm starting with, I get a new expression. So to go through and explain chemistry, I have to look at a new equation for every single problem. Is that a bit tedious?
Yes.
Yes. So what did we go through and do? We said instead of looking at leftover pieces, we said, is there a way we can just define it as all of our reactants get consumed all the way over to our products. How do we balance that system out? And that's the system of balancing that we worked with. That's how we get that expression. Right? Once we have this expression, we now have the ability to convert between these. If I take one of these,
You get two.
I have to get two of these. What does that mean? I see your hand. Give me a second.
Oh, yeah.
1 O2 equals 2 H2O. I have an equality. Now when I want to go through and convert the substance of O2 to H2O, I know I can use the chemical equation. What is the unit associated with those numbers? You can't tell me it's O2 and H2O. Right? One option is a mole. Right? The mole is a really large number, though, of what? Particles, whatever our substance is, or our piece. Okay? We name that piece O2. So we could go through and insert the unit of moles in here. That works. What else could we insert into that?
Atoms and molecules.
We could use atoms. In this case, atoms doesn't make sense because
Oh, yeah. Because there's diatomic.
both of those are molecules. They have more than one atom. Okay? Because the chemical equation tells us how many pieces go in. Our piece is just called a molecule. So by recognizing the substance and the unit, we can start to create a system that allows us to apply it out to everything we observe anytime we change the amounts of hydrogen, oxygen, or water. That's pretty cool. Right? Once we have that, that gives us an equality. Those equalities, we can then go back into dimensional analysis and play everything out. Right? So we're responsible for layering in these extra things. I can't give you all of the chemical equations in the world, okay, on top of all of the chemical substances in the world. It's not going to work. Okay? You have to come up with that layer of interpretation. So recognizing where to find those conversion factors becomes the trick. Okay? So not only are you using dimensional analysis, you also have to know where to find the conversion factors. Right? And this is why I think we're getting questions of, well, you just multiply by the molar mass. I don't know. Do you need to multiply by the molar mass? What are you converting? Okay? I've talked to several chemistry instructors, and they say the same thing. Students say, oh, multiply by molar mass. Well, like, I have no idea what the heck you're supposed to do with that. Okay? And that's because we as instructors literally do not know. We have to write out dimensional analysis to establish where the units go, to establish then conversion factors that allow us to move through. Okay? We have to look it up. We haven't memorized some magical system that works. We're just using the same process that we're trying to get you to use. Okay? But it can be hard to find those conversions, so we're going to address that in the next slide.
What are you talking about in relation to multiplying it to the molar mass? Where is that coming from?
So if I want a desired unit,
Yeah.
and I'm given some unit, okay,
Yeah.
students will say, well, I multiply by the molar mass, or I divide by the
You're
molar
trying to
mass.
skip all these steps.
Okay, and they just say, oh, that's what you need to do. Well, I don't know. I literally do not know
Yeah.
if you need to multiply by the molar mass. Maybe that wasn't necessary. Maybe you needed to use Avogadro's number. Okay? Maybe you needed to use inches to feet. Okay? The only way I would know that is setting up this process of checking those units. So the big thing we want is, number one, recognize our conversion system. How do we use that? The next part is recognizing where the conversion factors come from. Okay? You already have some cheats for you. You have on your first page of the exam conversion factors listed out. The conversion factors I gave you are to convert direct units and or just direct measurements. They don't convert substances. Okay? Some of those are also missing. Okay? But we've got a lot of conversion factors on here. So on your exam, you get all these conversion factors. You get the periodic table. This was really quickly put together. Okay? It might be useful for you to know where you can find these things, right? The periodic table gives you some information, right? What information does the periodic table give you?
Atomic weight, atomic
In
number.
molar mass.
Okay? The atomic mass and the atomic number. So what I would do is take thorium here as an example. Why would I pick thorium over any other?
Thor's cool.
Thor's cool. Sure, why not? Okay. Most of the periodic table, I'm going to need access to those numbers. I'm going to want to know what they are. How often are you going to use thorium on any exam? Probably not. Okay? So if I put notes down on that symbol, if I happen to overlap the numbers there, it's not going to be a big deal as long as I know the meaning of those. Okay? So I can circle that number on top. I can even write it like this, so it's a little bit bigger. What does that number on top mean? Many things. Okay, what are those many things?
Amount of protons in the atom.
The number of protons. What else does that mean?
It's the atomic number.
It's the atomic number. If that atom was neutral, could be the number of electrons. Okay. So by writing that information down, now if I see a question that says what is the atomic number for silver, I go back to the front where I wrote down atomic number is the number right above. I now find silver. Unfortunately, I had to have that memorized. Ag is silver. It's 47. I've got my answer. No thought process. It's just there. I have it. Okay. What is the number underneath? Okay.
Amount of neutrons and protons.
We have our atomic mass. Officially off the periodic table, it's our atomic mass and not our mass number. And we run into some nasty questions there. Take a look at the practice final. The mass number is the number of protons plus the number of neutrons. The atomic mass is, yes, it's also the molar mass. Okay. The atomic mass is AMU. What is AMU?
Atomic mass unit.
Atomic mass unit. It's a measurement. A measurement of what?
The average of all the.
That's getting to the larger point that I actually wanted on this. All of those are the average mass numbers. Okay. So the periodic table does not tell you the mass number, it tells you the average mass number for that element. Okay, so related, not the same. Okay, the atomic mass is useful. We heard something about AMUs. AMUs is a measurement of mass. Mass for what?
A single atom.
For a single atom. So really what I should be writing there is not AMUs, but AMU over atom. What have I now written?
Conversion.
A conversion factor. Okay? We could actually even take this a step further or backwards and say this is AMUs equal to 1 atom for that substance. In this case, thorium. I'm now providing a measurement tied to the substance. Okay? What was the molar mass? It's still from the same section. I've still got that number circled. It's still within that box.
232.4
What? 232 point.
grams
Grams
per
per mole.
molecule.
That is the grams of thorium, which is equivalent to 1 mole of thorium. Okay? So I notice a lot of you are listening to me. That's cool. I like that. I gave you a little sheet, right? That had the stuff on it, periodic table, where I said it would be really helpful to write this down so that when you have this problem and you're trying to say, well, I don't know what to use to convert, you can pull out the sheet and be like, oh, that's where that information is stored. I now know it. I can use it. Okay? If you don't write it down, what are you then doing? Sure, we could do all of that.
We'll just jump to that.
Some people are really good at that next part. What would you be doing if you don't write this down? No,
Just expecting.
not necessarily. The only reason you're wandering aimlessly is because you're not good at the first part, which is okay. A lot of people aren't.
I'm not.
Ensuring that you don't forget.
Has something to do with forgetting. It has something to do with the opposite of forgetting. It has to do with remembering this in your head, holding it, keeping that knowledge in your head so that you can then access it and use it. Okay? If you don't access it and use it, you will forget it. Okay? Guess what happens? Most of us are horrible at accessing and using it, particularly because most of you feel, which is probably not untrue, that you will never need chemistry again, okay? Which is probably true. The process of solving and getting through this, though, however, is a skill that you need. The point of using chemistry is to put it in a different language so that now you have to struggle through that process. You remember the process better so you can apply that process to an entirely different system more efficiently in the future.
It's kind of
Right.
more complicated.
So, great. We can now convert mass and moles. We can convert AMUs and atoms. Right? Because we got two new equalities. So all we've done so far is converted different measurement systems. When we look at an individual number in science, if I give you the number 42, what does that mean?
Many things.
It can mean many things because
No identifying.
there's no identifying extra information like
Like a symbol or the unit of measure.
how about a measurement? Right? 42, a measurement unit. What would be an example of a measurement unit?
Atomic number or
Grams, liters, seconds, moles. Right? Every number, skittle farts. Every number needs a measurement unit. Okay? So that's now 42 grams. That's not that bad. My son ate 42 grams the other day. He ate 42 grams of what? Oh, it was 42 grams of arsenic. Whoa! That's a problem, right? I shouldn't have let him do that. Why is that now a problem? Why are you now like, whoa, that's not good?
CPS.
Because arsenic will kill you. Is just knowing the measurement unit and the value useful?
Yeah.
It has some value. It's more useful than just the number. But by adding arsenic to the end of that, that went really bad for my son. If I said 42 grams of food, you're probably like, eh.
H2O.
I don't really know a comprehension of how much 42 grams is. Maybe that's okay for him to eat. Okay? But as soon as we say arsenic, you're like, nope, that's done. That's a bad idea. Okay, Mike, you're a bad dad. Don't do that. Okay? So numbers need a unit. They also need a substance. And when we're going through and doing chemistry, we're in the business of manipulating numbers and units, but we're also in the business of manipulating substances. This goes all the way back to the origins of chemistry with the Philosopher's Stone. What were they trying to do? Why was chemistry even created?
To make money.
Witchcraft.
To make gold.
To make gold. That was the whole point, was to convert lead into gold. And if they came up with a process to do that, we'd all be millionaires. Or the scientists. They weren't scientists at that point. The alchemists would then be millionaires. Okay, great. They could be the most wealthy, powerful people on the planet because they could do that conversion. Okay? They're converting a substance, lead, into another substance, gold. Okay? They need the power to do that. Okay? How did we do that? Or how did they attempt to do that? Well, could we come up with a notation to explain how they would try to do that? What are they starting with? Lead. Right? Ooh, PB. Why would I use PB? I want to use a symbol for lead because I'm lazy. I don't want to write out all the letters. Okay? I want to convert that into gold. How can I do that?
Take away 3 protons.
Okay, so I just do lead and gold. And that now makes sense that that's what I was trying to do. If I just wrote lead next to gold there, you're like, yeah, Mike was totally converting lead to gold.
Nope.
Okay, no. Fix my notation. Fix my language.
Put a line in there, an arrow, sorry.
Fix
No,
No,
no.
between the two,
Sounds like
starting at
it's
the
A,
B,
you want A.
starting at the
Horizontal line, horizontal arrow pointing towards a.
Okay? By adding just that simple symbol, what does it now start to demonstrate?
Explains that you're trying to turn lead into gold.
What I'm starting with and what I'm ending with. I have a reactant going to a product. That says product. Okay? I now have a basic notation on how to use this. As we manipulated or started to manipulate, we found that that equation was invalid. It didn't work. Okay? Why would that not work?
Things are missing.
Because it doesn't.
Why did we discover that that did not work?
Trial.
Tried to do it and it didn't work. What about this doesn't work? I can't just turn it into gold. Why can't I just turn lead into gold? What's the difference between them?
Three protons.
The number of protons. Okay? I can't just, remove protons from lead to make gold. It doesn't happen because protons don't exist on their own. Okay? So I have to modify this notation, okay, to bring it into a real world format. That's where I would end up with H2 plus O2 to H2O. This is still a reactant in a product. Okay? Is that better than what we had before?
Yes.
Yeah, the symbols at least show up the same. Or we have the same symbols on both sides. However, there's still a problem with it. What's that problem? It's not balanced. I'm destroying matter. Am I allowed to destroy matter? No. So how do I fix it? I change the coefficients. Okay? So what we're doing just on everything that we've written here is pretty much everything that's been covered this entire semester is now on this tiny little slide. Yay! Okay? All of this stuff you have to know and pull and draw access to. But I don't see people drawing access to it, so I'm trying to outline it again so that you can see it and start to recognize, oh, okay, that's useful. Okay? If I take a look at this chemical equation, what can I now do? Well, what is that substance that I'm just going to circle it on the screen?
Oxygen gas.
Oxygen gas. With that arrow, I can do what?
Turn it into water.
Turn it into water. You mean I can take oxygen gas and make it equivalent to water?
No, you need, well, first.
102 equals 2H2.
Assuming I have enough H2, yes, I can. But I would need one H2O, and I would need to make
Dos.
2 H2.
Dos.
H2O, sorry.
Good job.
Okay?
That was
That's a number and a substance.
we're missing.
We're missing the measurement unit. What's our measurement unit?
Molecule.
Molecules. A lot of people want to use molecules, and that is okay. It's perfectly all right to use molecules. Okay? We do run into issues with that because we can end up with fractional products, and that doesn't work. Okay? This is why chemistry said none of this fractional product, that doesn't make sense, and I can't control single molecules. I'm going to scale up to moles. That changes my equality ever so slightly, and I have a new expression now. What is special about this expression?
You can
have half moles.
Yeah.
I can have half moles. I can also convert the substances. Right? The stuff over here, grams of thorium, moles of thorium. Did I convert the substance?
Not the
The substance is thorium, just the measurement. Okay? AMUs to atoms, both of those were the same substance. No substance conversion. Right? Everything over here, there's no substance conversion. They're all measurements. Okay? This is why chemistry is cool. Chemistry takes all those standard crap measurements you did, and we can turn them into a different substance. Magic. Spirit fingers. Jazz hands.
Those were not spirit fingers.
Sorry. Okay. So, what's the extra piece of information here? We could layer in, just like we did over here. We've got our units. We've got these units. Okay. But if you just wrote down 1 mole of O2 equals 2 moles of H2O as a cheat sheet, that's not going to be very helpful, right? Okay. How did we get that information? How did we convert substances?
Making the assumption that there was an excess of H2.
A chemical equation converts substances. It says verts. Mola A to mola B. Thank you for that. What else converts substances? How much oxygen is there in sodium carbonate? How did you know that? That. Okay, from a subscript. We look at sodium carbonate, the subscript says 3. What are you looking at? Where did the subscript come from?
The balancing of
From the symbols,
What are the symbols representing?
the elements and their amount.
the compound.
In what? Our compound, yes.
Oh, sorry. Yeah.
Okay, but if I had just written sodium carbonate, because no one's saying it, you're going to make me write it. Sodium carbonate. Can you tell me there's 3?
No,
No, why not? What did you need?
you need to know the
You
symbol.
convert it to
and you
its,
compare
It's
it.
not a chemical equation, it's a chemical formula. So the chemical equation allows me to convert substances, so does the chemical formula. Right? With this, when we go back to our questions and we now say set up our step 1 and step 2, this is where we can then write in that middle, that conversion section, be like, I need to convert moles of O2 into grams of hydrogen. Is that a valid conversion factor?
Maybe you got to.
Grams and moles shows up on my cheat sheet. Where does it show up?
Measurements.
In the lower left-hand corner, where I'm converting the measurements for what? The same substance. Can I convert moles of O2 into grams of hydrogen?
Oh, no.
No, the substance has changed. I can't pull that information out easily, which means I'm going to have to use a sequence of conversion factors. Right? Recognizing that I need multiple steps can now help me move through this. Kinda, sorta?
Yes.
Confidence level. High, somewhere, bottom. Okay.
We say that until you leave us alone. Until the test comes around.
Well, and keep in mind, like what Mike's introducing, or what Mike's reminding you guys of, is that the periodic table and and all of this is supposed to be prior knowledge, stuff that you go into the test knowing, or at least being able to access because it's been encoded in the textual artifact of the periodic table, like we've been talking about in right. That there's a system, there's a logic behind this stuff, and it's stuff we've already covered in class. So you either have to be able to figure out how to decode it from the documents we covered in class or the documents provided, the periodic table or whatever, or you have to come in with the knowledge already in your head.
And that's, either of those work. Decode or have it memorized. Okay? The problem is if you memorized it, you're stuck inside your head, and your head is not a happy place. Okay? I do not want to see what's in your head. Likewise, do not get close to mine. Okay? So here's the question. What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed?
Bring it on.
Right?
Oh, do you want us to write it?
Yeah. Yes, I would like you to write this
We're
one.
going to walk through it together.
The walkthrough I will do is step 1, our dimensional analysis. Step 1, equal sign. What unit do we want?
What is the mass in grams?
Grams of NaHCO2.
are grams of sodium hydrogen carbonate. What am I starting with?
CO2, 2 moles of CO2.
2 moles.
Moles of CO2. Okay? The numbers are meaningless, so let's ignore the numbers. Measurement. What is the unit that I'm starting with? Moles. What is the unit I end with? Grams. Are those the same? No, so I have to do a conversion.
Yes.
Okay? Is it as simple as just converting the measurement?
No.
What is the substance? CO2 and sodium hydrogen carbonate. Those are two different systems. Right? Which means I'm going to have to do multiple conversions because I have at least two systems to look at. I have a gram and mole, the measurement is different, and I have a substance that's different. Okay? So this means I'm not going to be able to do this in one fell swoop. I can't because there's two separate systems functioning. Okay? Which do you want to bring in first?
Let's do what we did last time. Substance first. Let's do measurements.
Grams.
Okay. I think dealing with the unit system can be easier sometimes.
Since we want to end with.
Okay. It may not be a bad idea to change the substance first.
Yeah.
Okay. Usually the substance conversion is a bottleneck. Okay. And it bottlenecks through the chemical equation and moles. Okay. So we want to focus on getting the substance converted across. Okay. Which means I'm looking at CO2 somehow converting into sodium hydrogen carbonate. Those are my substances. What would the units be? Because I've got my cheat sheet where I wrote down where to convert substances, I know what those units are. That sounded like an awfully big question mark. Josh? Moles? 2 is a number. I don't want a number. I want the measurement unit. You gave me 1 again. That's a number. I don't want a number. I want the measurement unit.
I said what?
Moles?
Okay, are you asking me or are you telling me?
Moles. Moles. Moles, Mike, for CO2.
1 mole of CO2. There's 2 moles of moles.
Right. We now have a complete system here. Now I have to go out and find where that information is. Again, because I have on my cheat sheet that extra information on where to convert between moles and moles, I now know where to look. Okay? And by me, you. Your turn, finish it. Don't break my heart. Just so you know, I have been running under the assumption that everybody is pranking me and that the third exam is going to come out and you guys are all going to ace it and be like, ha ha, we made you think we didn't know it.
We get an overall A now, right?
I've really been hoping that that's what's happening. So, it's just one giant prank. Where do we find the conversion factor for our substances? The substance conversion factor comes from our chemical equation. Why do we know we only need the substance?
Only the substance because we're changing CO2 to...
CO2 to sodium hydrogen carbonate? Why are we not changing the measurement? Because you didn't. You didn't write the measurement.
Yeah,
the measurement didn't change. That's why. Okay? So you're just converting the substance across. We can do that through the chemical equation. We get that information from the coefficient from the chemical equation. What coefficient shows up closest to the sodium hydrogen carbonate?
2.
What coefficient shows up closest to CO2? 1. What unit would we now have if we ran this conversion?
2 moles of sodium.
What unit? Don't give me any numbers. Moles of sodium hydrogen carbonate. Okay. So, is that what I want for an answer?
No, you want grams for sodium.
So what has to happen to the moles of sodium hydrogen carbonate? It needs to be converted. Right? It needs to disappear. And ideally, what do I convert it to?
Grams.
Grams of sodium hydrogen carbonate. Okay? That's my ideal conversion system. Okay? The substance is the same, so that's just an observation. Substance is the same. The measurement changes. Where do I find the conversion factor that converts those substances?
The atomic number.
Periodic table.
That is the atomic mass, close,
Sorry.
from the periodic table. Officially, we don't want to use the atomic mass because the atomic mass was what units? AMUs. That is the atomic mass unit for an atom. Is a mole a single atom? No. So I don't want the atomic mass, I want the molar mass. That was slightly random. Let's take a look at sodium as a symbol. 11, and I'm just going to round. No, I'm not going to round.
We round. Round. 23.
I just need it so it doesn't look the same. That's the only reason. 22.99. Okay. So where do we find our atomic mass and our molar mass?
On the bottom, below the symbol.
That symbol. Okay. And what I had written out for you guys to write down was grams of sodium equals moles of sodium. Where does the 22.99 show up in that equation?
22.99 grams of sodium.
The number is our grams because it's a molar mass. The mass is the important part of that. The number gets associated with the grams. What gets associated with the moles? 1. Okay. We now have the mass for just sodium. We would need to get the mass for the hydrogen, the carbon, all 3 oxygens. Add that all up and drop that in. Assuming that the majority of you did that calculation correct, you end up with something like 84 and change. 84 grams over 1 mole. And we could now enter it on our calculator and we'd get a final answer. How are we doing with that?
Awesome. I don't want to say good.
Let's try another one and find out.
You're like the harbinger of great
Give
news.
us,
Yeah.
give us like.
Can you replicate the process? That's the biggest deal. Dominic.
Ready. Let's do another one.
Let's take a test. 2 moles of carbon dioxide. Do we multiply the 84 by 1?
So this is an interesting question. It said we are solving for 2 moles of CO2, so shouldn't I multiply the 84 by 2? Okay. The question comes is when are you trying to do that? At the end. It's already factored in. We already have the 2 in there. 2 times 84. It's already done. If you add and multiply the 84 by 2 a second time, you've now multiplied by 2 twice. This is the beauty of inserting it and not combining conversions. Okay. So, and we again need to be careful on this. So the next statement was, I don't need to multiply the 84. The conversion factor between 84 grams of sodium hydrogen carbonate and 1 mole of sodium hydrogen carbonate, you do not touch because that is a valid conversion factor. Okay? Does the number 84 need to be multiplied by 2? Yes, mathematically it does. So it's again focusing on what is your conversion and only inserting into that expression the exact given information. The instant you start to now combine systems, you screw the whole process over. Okay? And I can't stress that enough. That's where the biggest mistakes come in. Oh, it said 2, so I'm going to multiply by 2. Well, how do you know you weren't supposed to divide by 2? Ooh. Okay? Those are pretty big differences. Okay? And because you have me as an instructor, I've probably put that answer as one of your answer choices. Okay? You need to follow the unit systems. Don't start combining conversion factors. Okay? Keep them as independent and separate as possible. Okay? And with that, we're going to take a sort of minor break from all the numbers and look at our solubility very quickly. When we're looking at reactions, we've seen a couple phases. We've seen solids, liquids, gases, and what's the 4th phase that we've talked about? Aqueous. Okay? That aqueous phase means that water was present. So if I take this salt and I dissolve it in water, what I end up with is the ions, because I can color code. I would have some green ions floating around, and I would some purple ions floating around, and then I'd have happy old water floating somewhere in between. Okay? So what we're looking at here is the ability for water to dissolve a compound. What is going to help water dissolve a salt? Why would heat help water dissolve a compound? Why is kinetic energy helping? Why is moving faster help us?
Creates more space.
There's an interesting idea. What happened to the bond between the green atom and the purple atom? Reactant to product. It's not there anymore. It's broken. How do I break bonds? I add heat. That's why I can move from solid to liquid to gas, because what's happening? I'm adding heat and I'm breaking the bonds between them. What is happening when I dissolve a substance? I'm breaking the bonds. In the case of an ionic compound, I'm breaking the ionic bonds. So does it make sense that if I add heat that breaks bonds and add water that breaks bonds, I would break more bonds faster? Yeah. Okay. It doesn't always track that way, but it works for the most part. Okay. So what we're looking at is something known as a solubility curve. I can take a look at any given temperature. Notice we have temperature on our x-axis. And I can dissolve some amount of a substance. Okay. So if I take a look at, let's say, let's not worry about time. No, it removed time from the system. It doesn't really cross a line, does it? Well, dang it. Where's... Fine. We'll just make the point really big right there. Okay. So at 60 degrees Celsius, I can dissolve how much sugar?
300. No.
I can dissolve 300, it looks like, grams in 100 milliliters of water. Okay, so the amount of each of those things. So I'm interpreting that line. Could I dissolve 350?
No. Well,
Okay.
you can try.
According to this graph, what we're saying is water saturates at 60 degrees to 300 grams of sugar.
No.
Which means to get 350 grams of sugar, I'm above the amount that is possible to dissolve. So I can't get there. Right?
Unless you add more heat.
We'll address that in a second. What if I dissolve 250 grams? Is that possible?
Yes.
Yeah, or 200 grams. All of those are possible. So anything below that line will dissolve. Okay? As long as I'm not on the line, I could dissolve more. Okay? If I'm on the line, I've reached my maximum amount dissolved. The solution is now what? Saturated. I've put as much as can possibly go into it. So on that line, I am saturated. Below that line, what's the deal?
Unsaturated.
I'm now unsaturated because I could add more. I'm not at that full limit yet. If I somehow made it to the blue dot, I would then be supersaturated. Can we get unsaturated?
Yeah.
Yes. Can you be saturated?
Yeah.
Yes. Can you be supersaturated?
No.
Must be able to if it exists.
Must be super for it to be super.
The term won't exist. It's impossible.
That sounds like a really weird superhero. An interesting idea. Anybody made, what is it?
Kool-Aid?
Not Kool-Aid. Yes.
Cereal?
Rock candy. There's the word I was looking for. Anybody made rock candy? How do you make rock candy? You get water.
Get rocks and candy.
You add a bunch of sugar to it. It doesn't dissolve. So you boil it. You add a bunch more sugar until it's all dissolved, right? Then what do?
You let it cool.
Pour it into usually some kind of mason jar, and then you put a string in it, and then you let it cool down. What happens?
The sugar collects on the...
The sugar crystallizes on that string.
Why does
Why
it
would the
attach-
sugar crystallize out of that solution? Wasn't it all dissolved?
forced it out of itself and it needed to attach to something.
I go up to 100 degrees Celsius, I can dissolve 490 grams of sugar, right? 475 grams of sugar. Right? What happens as this system cools?
It unsaturates?
Wait, oh, the amount of sugar stays the same, so it like,
The amount of sugar has to stay the same in that container. So what happens as this cools? We move this direction, right?
and yes,
And where would we be?
yep.
At
Supersaturation.
We'd be in that supersaturated system. Ideally, we would probably drop all the way down to room temperature. Whoops, wrong eraser. Where's room temperature on this? Let's say 20.
20 something.
I thought Celsius 0 was room temperature.
No.
Freezing point. Wait, that's freezing point, I'm
point.
sorry.
I would now be well above that saturated line, right? Right? If I'm above that saturated line, I would now be supersaturated. Oh yeah. The water now has more sugar in it than it can physically hold. So what does the water start to do?
Force the sugar.
Meg's rocket.
Force the sugar out. Says, get out of here, I don't want you anymore, get out of my solution. And so what happens? The sugar goes, well, okay, I have to leave your solution. What phase is sugar, though?
At this point, it's liquid. It returns to
It's not a liquid, it's aqueous. Sugar in its own is a solid. So what happens? All of that sugar between our supersaturated point and our saturated point,
So is sugar and water a chemical reaction?
200, let's talk about that later. 275 grams of sugar crystallizes out of that solution. And there it is. So we have, in theory, a supersaturated solution. Can you generate supersaturated solutions in the real world? Yes, they do actually exist, and there's all sorts of fun things that you could do with those if you wanted to talk to me about it. You've actually done one already. You remember the idiot that stuck his hand in that jar?
Oh, yeah.
Yeah. What was that solution he stuck his hand in?
Sodium.
A supersaturated solution of sodium acetate. Right? It was so saturated that it was like, oh God, I need to crystallize, but it didn't have anything to grab a hold of until he stuck his hand in it. And it was like, oh, there's something to grab a hold of. And it grabbed a hold and crystallized out. Okay? That's why you saw all of those crystals. That reaction also was accompanied by a change in temperature, which burned his hand.
Why doesn't it attach to the glass?
It can. It usually depends on the glass. The glass has to be nice and smooth to prevent that crystallization. We can talk about that also if you'd like after class.
Like,
It's like why
why does
Mentos-
the surface area?
It's like when Mentos explodes.
You need a texture to it, yeah.
Oh, look at all that.
We could look at other curves. Every compound has slightly different systems. Notice, as we add heat, what happens? The solubility for each of those compounds does what? I add heat to sodium nitrate, it dissolves. More dissolves, more dissolves, more dissolves. Is it always true?
No.
Selenium sulfate doesn't always dissolve. Okay? In fact, as you add heat, it does the reverse and it starts to become less soluble. Okay? That would be a neat observation to talk about in another day. So, our solutions and how to measure them. So this is the next kind of big part that we need to move into. All right? How would I, so number one, what type of reaction is this? It's a double replacement. Good. We have to be able to acknowledge that. Okay? Here it's not as big of a deal to acknowledge because I predicted the products and I balanced it for you. How do we quantify the amount of silver bromide used or produced? Where's silver bromide in this?
It's both sides.
Silver bromide is not on both sides.
It's on the right side.
It's on the right-hand side. It's the product. How would I quantify the amount of silver bromide produced?
The coefficient.
Yeah, I go into the lab. I want to quantify that amount. Why grams? Thank you.
Because, oh, sorry.
Like I know why.
Why grams?
Because it's a solid.
Because it's a solid. It's the only one that's a solid. Solids we measure by mass. Okay? If I was going to try and predict how much of that solid was formed, based on the amounts of materials I put in, I could go through and say, well, the grams of aluminum bromide or the grams of silver nitrate added to this. Why does that become a problem for this equation?
Because on the left-hand side, you only have liquids.
Do I have liquids on the left-hand side?
No, I mean,
I have aqueous. So if I measured the grams of aluminum bromide, what am I measuring the grams of?
Aqueous.
Elaborate on aqueous. Yes. The grams of aluminum bromide and the grams of water. Is water producing silver bromide? No. How do you know that?
Because
it's solid.
It's not in the chemical equation.
Oh, of course.
How would I quantify then the amount of aluminum bromide? I would need to know the volume potentially. But then what am I measuring with the volume? Am I measuring the volume of silver bromide? I'm measuring the volume of silver bromide and the volume of the water. So that doesn't fix it perfectly. What I would need is another conversion factor.
dissolve the water?
Anybody heard of ABV? What does ABV mean?
Alcohol by volume.
Alcohol by volume. It's the amount of alcohol by volume with an individual substance.
Such confidence.
So this is why you can go out and you can look at cans that say ABV on it. Why do they need to say that?
You drink responsibly.
So that you can drink responsibly. When you go out and it says 4.5 ABV, you get an idea, maybe I can drink 2 of those. If it says 95 ABV, you should be like, yeah, maybe I won't drink so much of that. Right? It's a way to monitor the amount of the substance and the volume of the solution. Why do chemists use molarity and not, for lack of a better example, ABV? ABV is by volume. What is the phase of ethanol? Liquid. What is the phase of water? Liquid. How would we measure those substances? By volume. That's why we do ABV. Why do chemists do molarity and not something by volume? Not everything is liquid. So we could do grams per liter. Not everything is solid. What's the first step in all of the conversions that we've been doing?
Finding its
Okay. So we want to know the final substance, right? Okay. Typically we started with a different substance. How do we convert substances? With a chemical equation. And what unit system did I need for a chemical equation to be useful? Moles. Why do chemists use molarity?
Because we're dealing with chemical.
Because I'm dealing with chemical equations and trying to convert the substances, I want moles. Molarity will be a given piece of information. That's what we would work with to deal with our conversions. You are now responsible for a new conversion factor. We will pick up there on Tuesday and we'll add another conversion factor with gases, and then all hell will break loose with more difficult questions.
When is our next